This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Today's discussion centers on a research paper investigating the role of visual processing versus factual recall in multimodal large language models, MLLMs, when answering questions about data visualizations. The authors challenge the common assumption that MLMs process visual information like humans. What are the core findings of this research?
The core finding is that MLMs often answer visualization questions correctly without actually interpreting the visualization. They leverage their vast knowledge base, recalling facts from their training data rather than relying on visual processing. This raises serious concerns about the validity of current evaluation methods for MLMs in visualization tasks.
This challenges the fundamental assumption underlying many visualization literacy tests. How did the researchers demonstrate this recall phenomenon?
They conducted experiments across multiple datasets, VLAT, VILA, ChartQA, using GPT-4o. They compared the model's performance with and without providing the visualization. In many cases, the model performed similarly well or even better without the visual input, indicating a strong reliance on factual recall.
That's quite surprising. What implications does this have for the design of visualization question answering these QA datasets?
It highlights the need for more rigorous evaluation methods. The current VisQA datasets may be inadvertently rewarding factual recall rather than true visual understanding. The authors propose a sanity check framework to address this.
Can you elaborate on this sanity check framework?
The framework uses a decision tree and a sanity check table to disentangle the effects of seeing, visual processing, and recall, factual knowledge. It systematically analyzes the model's performance under different conditions, with and without the visualization, and with and without contextual information that might trigger recall.
What are the three key failure cases identified by this framework?
Case 1 identifies inherent model biases, where the model answers correctly even without any information. Case 2 indicates that recall positively influences the answer, meaning the model relies on prior knowledge. Case 3 shows that recall negatively impacts the answer, suggesting conflicting information between the visualization and the model's knowledge.
How did the researchers apply this framework to the different datasets?
They applied the framework to VLAT, VILA, and ChartQA, revealing varying degrees of recall influence. VLAT and VILA showed a high reliance on recall, while ChartQA showed less. They also created a synthetic dataset, VWhite Forge, with non-factual data to further investigate the impact of recall.
What were the results with the VWhite Forge dataset?
VLAT Forge, with its non-factual data, showed that recall could negatively impact performance. When the visualization contradicted the model's prior knowledge, the model's accuracy decreased. This demonstrated that the model was indeed relying on its factual knowledge base.
Did the researchers attempt to mitigate the recall problem through prompt engineering?
Yes, they tried prompting the model to focus on the visualization. However, this proved ineffective, suggesting that simply instructing the model to ignore its prior knowledge isn't a sufficient solution.
So, what mitigation strategies do the authors propose?
They suggest several strategies: quantifying the prevalence of recall using their sanity check framework, avoiding questions with factual data, designing counterfactual scenarios, regularly monitoring and updating datasets, and exploring more sophisticated prompt engineering techniques.
What are the limitations of the proposed sanity check framework?
The framework assumes that context can be easily removed or modified, which isn't always possible. Aggregating results across questions can mask nuanced effects at the individual question level, and the experiments were primarily conducted with GPT-4o, limiting generalizability.
What are the broader implications of this research beyond visualization understanding?
The findings highlight a broader issue in evaluating the visual capabilities of MLMs. Similar recall problems might exist in other modalities and datasets. It underscores the need for more robust and nuanced evaluation methods for all MLM tasks.
The authors mentioned the black box nature of these models as a challenge. How does this affect the interpretation of their findings?
The inability to directly inspect the model's internal workings makes it difficult to definitively determine the exact mechanisms behind its decision-making. The sanity check framework focuses on identifying problematic cases rather than explaining the precise internal processes.
What are the next steps for research in this area?
Future work should extend the sanity check framework to other MLMs and datasets, develop automated methods for modifying context and visual elements, and explore the use of adversarial examples. Investigating cross-modal evaluation strategies is also crucial.
The paper emphasizes the importance of rigorous evaluation in the context of rapidly advancing MLLM technology. How does this relate to the broader field of AI development?
The need for rigorous evaluation is paramount in ensuring the trustworthiness and reliability of AI systems. Without careful evaluation, we risk deploying models that perform well on benchmarks due to unintended biases or shortcuts, rather than genuine understanding.
The authors highlight the potential for overestimation or underestimation of MLM capabilities due to recall. Can you elaborate on the specific scenarios where this occurs?
Overestimation happens when a model's high performance is attributed to visual understanding when it's actually due to recall. Underestimation occurs when a model struggles because its recall conflicts with the visual information presented. The sanity check helps identify these scenarios.
The study uses GPT-4o extensively. Are the findings likely to generalize to other MLMs?
While the authors observed similar behavior in other models, further research is needed to confirm the generalizability of these findings. Different MLLMs may have varying degrees of reliance on recall.
The paper mentions the use of a chi-square test for statistical significance. Why is this appropriate in this context?
The tri-square test is suitable for comparing observed frequencies, e.g., correct versus incorrect answers, with expected frequencies under different experimental conditions. It helps determine if the observed differences are statistically significant or due to chance.
The authors discuss the limitations of removing context. Are there specific visualization types where this is particularly challenging?
Yes, choropleth maps are a good example. The geographical shapes themselves often encode contextual information that's difficult to remove without altering the visualization's meaning.
The study focuses on disentangling seeing and recall. Are there other factors that might influence MLM performance in VisQA tasks?
Absolutely. Factors like the complexity of the visualization, the clarity of the question, and the model's training data all play a role. The sanity check framework focuses on seeing and recall, but acknowledges the influence of other factors.
This has been a thorough discussion of the paper's key contributions and implications. Thank you.